So first of all, I'm most grateful to the organizers, especially the local organizers, for their really hard work for this conference and inviting me with all my heart. Secondly, I'd like to apologize to those who heard my talk last December because there's some overlaps here. Okay, so I hope you have forgotten my talk last time. If you didn't, look at my eyes. I'm going to mesmerize you. Okay, so first of all, let me introduce the problem here. It's very simple, very classical, elementary. So suppose X is a smooth projective variety, always over C. Okay, so what I want to think about is the space of all smooth rational curves in X. Curves of degree D in X. That's what I want to think about. So as most of you know, that this is not compact. Even for nice spaces like projective spaces, for degree D greater than or equal to 2. And there are millions of reasons to ask for a compactification of this space. Right? So many reasons to ask for compactifications. Luckily, we know there are many compactifications here. Let me state first a few nice compactifications. I'm going to explain why I think these compactifications are nice later. First compactification, I think, and most famous compactification is due to Grothendieck, and it's called Hilbert scheme compactification. This is Grothendieck, 1960s. Okay, how do I compactify this? You think about all possible ideal sheaves of the structure sheaf of X. Okay, or what is the same thing is to think about the closed subschemes of X with fixed Hilbert polynomial, in this case dm plus 1. And Grothendieck proved that there is a projective scheme structure on this set, projective scheme. Certainly, if you have a smooth rational curve in X, then you have a point in the Hilbert scheme. So R embeds into the space into the Hilbert scheme. So what I can do is to take the closure in the Hilbert scheme. So let me denote it by the bold H. That's the closure of R in the Hilbert scheme. I'm going to call this Hilbert compactification. Okay, the second compactification, I think second most famous compactification, I think is the stable map space. Okay, I think this is due to Kontsevich and Manin, 94. So what do we do? M000 bar XD. That's the notation, standard notation for stable map space. We think about all possible morphisms from C to X. And what is C? This is connected nodal curve and genus 0, arithmetic genus 0. Okay. And the conditions are this. So we think about the fundamental class. So C is nothing but the union of spheres. You can think about fundamental class of the spheres and then take the direct image or push forward of this fundamental class. And the requirement is this should be D in the second homology of X, second integral homology of X. And then the stability condition is that the automorphism group of F should be finite. And we take the isomorphism classes. And it's proved that this is projective scheme, projective the Lim-Mumford stack. projective moduli space. Right. Certainly, if you have a smooth curve inside X, smooth rational curve, then you can think about inclusion map, inclusion morphism. Obviously, this is stable. The automorphism group is just trivial. So I have an embedding of R into this stable map space. Why don't I take the closure here? So let me call this, let me denote this by M, which is the closure of R inside the stable map space. Let me call this conservative compactification. Okay, so this is another nice compactification of the space of smooth rational curves inside projective variety. Okay, this is second compactification. And what about the third one? Third one is probably the third famous compactification. This is by Bistable Sheaves. This is by Carlos Simpson in 1994 again. So there is very general construction by Simpson. So he thought about the following. Let me denote it by simp Tm plus 1x. So this is the set of all stable, more precisely semi-stable sheaves on X with Hilbert polynomial, given Hilbert polynomial, Bm plus 1, and we take the equivalence classes. Simpson proved by GIT, it's quite surprising, it was very surprising at that time, that this is a projective scheme. There's projective scheme structure, yeah. Okay, so let me remind you what the stability here. A coherent shift F on X is called semi-stable or stable.
Let me have one.
Yep.
So that's not surprising. I mean, any GIT quotient is projective by definition.
Right. I mean, the surprising part is the calculation of stability.
Simpson proved that there is a bounded family, that this family...
Oh, yes, right. You're right. Sorry. So anyway, that's not the main point of my talk. So two things, boundedness and the calculation of stability. So a coherent sheaf is stable if the following two conditions are satisfied. For any non-trivial subsheaf f prime of f, first of all, the dimension of the support of f prime should be equal to the dimension of f, the support of f. Secondly, Hilbert polynomial of f prime divided by its leading coefficient should be smaller than the Hilbert polynomial of f divided by its leading coefficient for m sufficiently large. So that's the stability condition. Certainly, if you have a stable sheaf, if you have a smooth rational curve inside X, then you can think about the structure sheaf of C. Then this is a stable sheaf. So certainly R is contained inside this moduli of stable sheaves. So I can take the closure here. So let me denote it by S. This is the closure of R inside the Simpson moduli space, and then we call this Simpson compactification. Okay, so the problem that I want to think about in this talk is this. I want to compare these compactifications. I want to compare the Hilbert compactification, Simpson conservative compactification, and Simpson compactification. Okay, right. So this is what I want to talk about here. So why am I interested in this problem? So let me explain the motivations here. First motivation is probably many of you know is log Moduli program. So inside the conceptual moduli space, we can think about the boundary divisor. So this is the locus of all stable maps from connected nodal curve C to X, and C is reducible. So this is a boundary divisor. And then, you can think about the log canonical model of M. This is defined as the product of the direct sum M greater than or equal to 0, H0, M, and M times Km plus alpha delta. Right. In a really surprising paper by Dawei, 2008, it was proved that when X is projected to P3, and when degree is equal to 3, that M and H, the Hilbert compactification, in this case this is isomorphic to Simpson compactification. These are related by log flip. Okay, more precisely, H is log minimum model, log canonical model of M for suitable choice of alphas. So motivation is to have a better understanding of this birational morphism. Another paper by Dawei and Koskun last year, they proved that when X, the target S, is Grassmannian, GR24, Grassmannian 24, and for conics, they proved the following. So with Kontsevich compactification, Hilbert compactification, they are related by explicit blow up and blow down. One blow up, one blow down. And then there is one further blow down to GR36. These are all blow ups. So, what can we do for higher degrees or more general Grassmannians? Not just GL24. That's a question one can ask for. So, but actually, that was not my motivation here. So, I didn't know Dawei's work when I started this project. So my true motivation here is different. So my true motivation was for curve counting invariance. So I was working with Jun Lee about Gromov-Witten theory, and then I thought that maybe I learned about the comparison result of Gromov-Witten and Donaldson-Thomas invariance, and I wanted to think about how to compare the invariance. Okay, so let me give you a quick introduction for curve counting invariance, because there are some graduate students in the audience. So let me start with a very classical problem here. Suppose X is a quintic alpha surface in P4. The classical problem is to find the number of curves, number of lines in X. Is a problem of the 19th century. It was solved a long time ago, but it gives you, it's a very good model for all enumerative invariance. Okay, so how do you solve this problem? Here's the way. In step 1, we ignore X. We think about P4. We find all lines in P4. Think about the set of all lines in P4. As everybody knows, it's the space of Grassmannians, is the Grassmannian of two-dimensional subspaces in five-dimensional vector space, GR25, right? That's the first step. We find the space of all lines in P4. What is the second step? The constraint is that the line should lie in X. That's the constraint. Constraint gives you a cycle in the moduli space. So the constraint is that L should lie in X, not just P4. Okay, so let's call sigma the defined equation of X, P4, or 5. This is the defined equation here, defined equation of X. Okay, and then you think about the universal rank 2 bundle over the Grassmannian GR25, and then projectivize it. Let's call it pi. And then there is morphism to P4, universal morphism F. Right, then you think about the constraint. L belongs to X. What does that mean? It's equivalent to saying that the defining equation should vanish. So, okay, so let's suppose I have a point L inside Grassmannian, which represents a line in P4. So it's the same thing. L belongs to L is the same thing as saying that the pullback of sigma restricted to L should vanish identically. But that's the same thing as saying that pi lower star F upper star sigma, the section, this is 0 at the point L. But what is this? This guy is a section of pi lower star F upper star O5. This is a vector bundle of rank 6. So, in the third step, what do we do? This is the constraint, this is a cycle that we have found. So, all we need to do now is by Poincare-Hopf theorem that we conclude that the number of lines in X is nothing but the cap product of the fundamental class of the Grassmannian with this rank 6 vector bundle. Top-Chan class, I'm sorry. Euler class, Top-Chan class. So this is how we define the curve counting invariance. So the first step, we need the moduli space. We first construct the moduli space. Secondly, we interpret the constraints as cycles. And thirdly, we take the intersection numbers of the cycles inside the moduli space. That's how we define curve counting invariance. But there are some delicate issues in defining curve counting invariance. What are the issues here? In order to do intersection theory, everybody knows, this moduli space should be compactified. Should be compactified. Otherwise, you don't get a nice intersection theory. So this compactification is the first issue here. The second issue here is that usually there are certain properties that we require for curve counting invariance. In most cases, what we require is the deformation invariance, which basically says that if you deform the complex structure of X, then the curve counting invariance should remain constant. Furthermore, the expected dimension of the moduli, there are expected dimensions for moduli spaces. Usually they are different from the actual dimension of the moduli spaces. Okay, so these two issues should be handled in order to define the nice curve counting invariance. Right. Okay, so let me talk about these delicate issues here. Okay, first of all, first issue is the compactification issue. Okay, so as I explained, there are many ways to compactify the space of curves. Okay, for instance, you can use a stable map space to compactify the space of curves. And if you do the intersection theory on modular curves, then everybody knows we get Gromf-Witten invariance. It's due to Kontsevich, Manin, and the virtual cycle is due to Li, Tian, Berendt, Van Teke, and also. And another way is to use the space of stable sheaves. Then you get the famous Donaldson-Thomas invariant due to Thomas in 1997 in his thesis. Also, you can think about Hilbert scheme of curves. If you have a curve inside a projective space, then you can think about the ideal sheaf is a stable sheaf. So this can be thought of as a special case of the moduli stable sheaves. So this is also called the Donaldson-Thomas invariant. There are other compactifications, such as moduli branch varieties, due to Alexeyev and Knudsen. But unfortunately, there doesn't seem to be a perfect obstruction theory, so I don't know what kind of deformation invariant curve counting invariance it can give. Nobody knows. No one seems to know so far. Also, there's compactification by stable quotients. Basically, this is using Grothendieck's code-scheme construction. Nicely, for certain choice of stability, there is a nice curve counting invariance, which I call MOP invariant, Marian Opria Pandari Pandey invariant, last year. It's a nice curve counting invariant. And possibly you can also think about some decorated sheaves.
And that was generalized, right?
Oh yeah, by Toda. Yes, yeah. Well, that's a very small generalization. Okay, and so furthermore, you can think about some other decorated sheaves. Moduli of decorated sheaves. Here, for stable quotient, so stable. If you have a stable map, you have curve, and you have a line bundle, and you have certain number of sections. Now, stable quotient is obtained if you loosen your condition. If you lose your, if you make your condition weaker. You allow your line bundle to be torsion-free. You allow torsion-free sheaves as well. Then you get stable quotient. On the other hand, you can keep the locally free condition, and you can allow the surjectivity to make it weaker. Then you can think about compactification of decorated sheaves. And I believe there's, with some nice choice of stability, there's a nice curve counting invariance, and this is investigated by my student in his thesis. Anyway, so there are many compactifications. For some not all compactifications are equal. So some compactifications give us nice curve counting invariance. Some may not. So why is that? Why some compactifications give us nice curve counting invariance, some not? It's because of the second issue here. So second issue is deformation invariance. Okay. So the standard way of handling deformation invariance is these days is to use the theory of virtual fundamental class. Due to Li-Tian Ferenc-Panteki, yeah. Okay, and what they proved is the Li-Tian Ferenc-Panteki is the following: if you have a perfect obstruction theory, something called perfect obstruction theory, then you automatically get a perfect virtual fundamental class. This is automatic. Okay, so virtual fundamental class in a nutshell is that is a homology class in the moduli space of the expected dimension, which is deformation invariant in certain sense. Okay, there is black box which gives you a virtual fundamental class once you know the perfect obstruction theory. What is perfect obstruction theory then? So perfect obstruction theory is nothing but a morphism in the derived category of the moduli space. So you think about cotangent complex of the moduli space M. So that this complex contains all the information about tangent, deformation, and obstruction theory of M. And then this is a morphism in the derived category of M, coherent sheaves on M. So two conditions. First condition is perfectness. What does that mean? Locally, état locally, this is perfect. What does that mean? So E is isomorphic to a two-term complex of locally free sheaves, concentrated in degrees -1 and 0. Only two terms in degree -1 and 0. Second condition is the obstruction theory, perfectness and obstruction theory. What does that mean? H0, let's call this phi. H0 phi should be an isomorphism. This is tangent space. And H minus 1 is the obstruction space, and should be surjective. These two conditions are perfect conditions for perfect obstruction theory. So you get a nice curve counting invariance once you have a compactified moduli space with the perfect obstruction theory. But it's very difficult to find perfect obstruction theory. It's a very strong condition. It's hard to find the moduli space with the perfect obstruction theory. Once you find a moduli space with perfect obstruction theory, then you get a new curve counting invariant. Right, that's all you need to do. Okay, so definition is fine. Just a compactified moduli space with perfect obstruction theory, then you get a curve counting invariant. But the key issue here is how to calculate the curve counting invariance. That's a very, very difficult issue. So, but as I said, curve counting invariance is defined now. How do we define this? So there is an artificial homology class on the moduli space, and the curve counting invariants are defined as the cap product of cycles with respect to the virtual fundamental class. So the key issue for calculating curve counting invariance to handle the virtual fundamental class. How can we handle virtual fundamental classes? So there are various methods here. Okay, so the most famous and most powerful technology for handling virtual fundamental class is something called localization by crosssection. So this is due to Kontsevich and Giventhal and Graeber, Pandari, Pandey, and so on. And secondly, so basically saying this: if you have a torus section on X, then it induces a torus section on the moduli space of curves, and then virtual fundamental class localizes to the locus to a neighborhood of the fixed point component, fixed point locus. Secondly, there is a technique of quantum Lefschetz and Grothendieck-Riemann-Roch theorem. So it's really as in the example here, in the example here. So you want first embed we want to think about curves in X, but that's very difficult. So you think about the space of all curves in projective space, which contains X as a hypersurface, and then you intersect the Euler class of pi log star f star or phi. So a formula of this kind is called quantum Lefschetz formula. And to calculate this Euler class, you can use Grothendieck-Riemann-Roch theorem. So this is the technique. But this works for genus 0 case, because the moduli space should be smooth to make this argument work. For this, you need the torus section. This is also a very difficult condition. To have a torus section on your variety, this is a very restrictive condition. Third technique is the degeneration technique, due to Jun Lee in algebraic geometry and the Ionel and Parker in symplectic geometry. But I heard that there is a gap in the symplectic geometry proof. So essentially, there is only one proof for the degeneration method. So basically, it tells me that if you have Calabi-Yau threefold, you can degenerate into the union of two simpler varieties, X, Y1, Y2, and the virtual cycle of X can be calculated in terms of the virtual cycles of Y1 and Y2. That's what this formula is saying. So for instance, Okonkov and Pandey could calculate all the Gromf-Witten invariants of curves, the NX is a curve, by using this method, because you can degenerate a genus G curve into the union of two curves of lower genera. Then you can use induction to finish the calculation. Okay, the fourth method is a new method. I'm very happy to introduce. For this, you need a very nice degeneration, which is not always given. The fourth method is a new method. It's kind of advertisement for my work. There is a method of localization by cross-section. This is a new method due to Jun Lee and myself. What's this method? You take the dual of E and then take the H1, first cohomology, then you get the obstruction sheaf of the moduli space. And suppose you restrict it to an open subset U of M, and suppose you have a surjective homomorphism to a locally free sheaf. Okay, then this technique tells me that the virtual fundamental class localizes to the complement of U. So that's somehow this is very efficient for some X. So this has support in the complement of U. So this may not look very impressive, but recently this year, Maulik, Pandey Pandey, and Richard Thomas used this technique to prove the very famous conjecture, which is called Katz-Clem-Waffa formula, which basically counts the number of curves in the K3 surface, curves of given genus. They could prove this formula by using this technique, by using our technique. This is posted in the archive in January of this year. Very surprising. So what is Katz-Clem-Waffa formula? This is a generalization of the famous generalization of the very famous Yau-Jaslow formula, which counts the number of genus 0 curves in K3. The KKV formula generalizes this. This is only for genus 0. This is for arbitrary genus. Right. It's very surprising, very interesting. I'm very happy to have an application of our method. Beautiful application. It's it's a very long paper, 85 pages long paper, but the proof is extremely beautiful. And I love this method. Degeneration, yes. You're right, yeah, degeneration. You degenerate your K3 surface in the union of two rational surfaces. Right, but they need to define a reduced Gromov-Witten or reduced Pandey-Thomas invariance, and that's obtained by this method. Okay, and another application that we are working on, so the main motivation for this method is this. What we are working on is this. We are trying to give so this is an ongoing project with Jun Lee and myself. We are trying to give a generalized Donaldson-Thomas invariant. What does it mean by generalized Donaldson-Thomas invariant? Thomas could define a DT invariant for the case when the stability equals semi-stability. But we can generalize this definition to the case when stability is not equal to semi-stability. And the method is by current blow-up, and this reduced, and this method of localization by cross-section, by current blow-up. So current blow-up effectively removes strictly semi-stable points, and then you can use the localization by cross-section method to reduce the virtual fundamental class, and then you can define for generalized Donaldson-Thomas invariant. Number 4. And then we can study the wall crossing. As you change the stability condition, Donaldson-Thomas invariant varies, and you want to compare the Donaldson-Thomas invariance as the stability condition changes. So actually, I should mention that there is already there is a definition of generalized Donaldson-Thomas invariant by Joyce and Song, very famous paper, about 200 pages long. But our definition of generalized Donaldson-Thomas invariant is different. in Joyce-Song approach is this. You decompose your moduli space into little pieces by Harder-Narasimhan filtration. And then you use the gadget of combinatorial gadget of whole algebra, and then you somehow give some weights and combine the numbers. We are not very happy with this approach because we don't want to break the moduli space into little pieces. I mean, we want more geometric definition of curve counting invariance. We keep the moduli space as a whole, but we keep blowing up the moduli space until you get the stability. Until you can remove all strictly semi-stable points. Okay, and then you can. So we can give a new definition of generalized Thomas invariant, and in some sense, our walk crossing formula is a lot simpler than Joyce-Song approach. Okay, so this is kind of advertisement for what I have been doing for last 6 months. Okay, let me go back to the original problem that I posed in the introduction part of my introduction. Right. So, okay. So the problem was to compare the compactifications by Hilbert scheme, stable map space, stable sheaves space, and so on. The reason I thought that the compactification by Hilbert scheme, stable sheaves, Hilbert scheme are important because that they give us curve counting invariance. Of course, you can think about other compactifications, but they may not give you a curve counting invariant, right? So that's why I thought H, M, S are important. So it's reasonable to start with the simple cases, right? So we start with the projective space case. X is projective space. The target is projective space. Okay, so how do we compare these compactifications? All right, so we'll first compare the Hilbert compactification with the Simpson compactification of moduli of stable sheaves. Okay, so it makes sense to start with the simple cases. When degree is equal to 1 or 2, then it's really easy. H is isomorphic to S, right? Because the structure sheaf of a conic is a stable sheaf, so there's nothing to do here. The first non-trivial case is when D is equal to 3, and this is due to Chung and myself. First non-trivial case. Suppose degree is equal to 3 and our target is projective space. Then we prove that there is a morphism from H to S. There is a morphism, and this is not just every morphism is really a smooth blow-up. Okay, and what is the blow-up center? Which is delta S. And so that's the locus of planar stable sheaves. The stable sheaves whose scheme theoretic support is contained in the plane, in a plane. Okay, and you can track that this is actually a smooth variety of codimension R minus 2. So this is the theorem. So as a corollary, immediate corollary, we can obtain a theorem of Freimuth and Trautmann, which appeared in the American Journal of Math 2004. This is the main theorem of their paper. They prove the following. If degree is equal to 3 and target is P3, R is equal to 3, then they proved H is isomorphic to S. Sorry, S. Hilbert scheme is isomorphic to the Simpson moduli. I mean, the irreducible component of Hilbert scheme is isomorphic, containing smooth curves is isomorphic to the Simpson moduli of stable sheaves, the irreducible component of moduli of stable sheaves. Why do I say this is a corollary? Because when R is equal to 3, codimension is 3 minus 1 is equal to 1 is already a divisor. So this is just an isomorphism. This is the immediate corollary of the theorem here. Okay, so how do we prove this theorem? This is, in some sense, is a very standard technique for those who worked on moduli of sheaves. The idea goes back to Langton's proof of properties of moduli of semi-stable sheaves. Okay, and it's a standard technique called elementary modification. Okay, so here's the idea. Let me explain the idea here. So there is a rational map from H to S. How do we get this? So if you have a curve closed subscheme in PR, the projective space, you associate the structure sheaf. So it's a coherent sheaf on PR. So what is the undefined locus of this rational map? Okay, so in other words, for which C, OC is not stable? That's the question. But you can easily prove that the undefined locus is really a divisor, smooth divisor in H, which I call delta H. This is the locus of curves, which is planar. C is planar. Planar cubic curve plus a point, embedded point. Okay, so this is a locus. Maybe in Dawei's talk, this kind of picture appeared. You have another cubic curve in a plane, and then you have an embedded point at the singular point. Embedded point. This is a picture here. Okay, I must emphasize that this is smooth divisor. Oh, by the way, this space H has been studied by Schlesinger, Kiem and Schlesinger in 1980s. Okay, so many things are known about H. In particular, H is smooth, well, we know that the delta H is smooth. Okay, so in this case, what's the problem? So if you have a point C in delta H, what is this? So there is embedded point delta P. Let's call this point P, and let's call the whole picture C, and let's call the planar cubic curve C prime. Then you have a short exact sequence. The structure sheaf of C goes to the structure sheaf of C prime. It goes to 0. And well, it is immediate to see it immediately follows from the stability condition that this is destabilizing. This is not stable. How do we get rid of destabilizing subsheaf? There is a standard technique called elementary modification or Kiem modification. For this, you need a family of sheaves. Okay, so you start with the universal family over H cross PR over H. So goes to 8. This is a universal family. Okay, and what do? We take the structure sheaf. So this is a family of sheaves on PR parameterized by H. Okay, then what do? We take the following. We let F be the kernel of the following composition. We take the structure sheaf OC, and then we restrict this guy to this undefined locus of delta H. So delta H cross PR. This is still a divisor. And then, so the elementary modification method, to make this method work, you need a divisor here. Anyway, but luckily we already have a divisor. And then this C prime forms a family. So you think about OC prime. So this surjective morphism, you compose these. And then take the kernel. And what is the effect of this kind of technique, the elementary modification? The result of elementary modification is this. You interchange sub and quotient sheaves. That's the effect of elementary modification. So after this modification, what you get is this is a stable sheaf. OC prime goes to OC. It's a non-trivial extension like this. So it's certainly a stable sheaf. In fact, this is isomorphic to the direct image of the normalization, the structure sheaf of the normalized C prime. C prime tilde. Anyway, this becomes a stable sheaf. All right, so elementary modification. After the elementary modification, everything becomes stable. This family of stable sheaves. So we get a morphism from H to S. From H to S. And then you analyze this morphism. Okay, so if the exceptional locus is the divisor delta H, and it goes to delta S. And you track that this is a projective bundle of, and the fiber is PR minus 3. And then you check that the normal bundle of delta H restricted to the fiber PR minus 3 is just O minus 1. And that tells you that this is a blowdown. Right, so in some sense the proof is not surprising at all. I mean, if you worked on the moduli of stable sheaves, then it's something that the technique has been known for many years. But just a careful analysis of these moduli spaces is necessary. Okay, so that's the easy part of the comparison result. Difficult part is comparing the Kontsevich and Simpson. This is the hard part, non-trivial. This is just a simple blow up, but the hard part is comparing M and S. Okay, so we start with the basic birational map from M to S. That's fine. How do we get this? So if you have a stable map from nodal connected curve C to X, so in this case projective space, PR, what do? We take that direct image. We take the most obvious sheaf, coherent sheaf, by taking the direct image. Okay, and then for if C is a smooth rational curve in PR, certainly this is a stable sheaf. All right. So what is the undefined locus of this rational map? Is really the locus where F lower star OC is unstable. Is really the locus where F has multiple components. Why is that? Okay, for example, suppose you have a morphism from P1 to a line L in PR. Suppose this is a D2-1 map. What is the direct image of the structure sheaf? It's a very simple exercise. The structure sheaf direct image is just OL plus OL minus 1 D minus 1. So this guy is destabilizing. The slope of this guy is too big. So if you have a multiple component in your stable map, then it gives you an unstable sheaf. So how do you handle this? So the strategy is the same. Very simple. So we find the locus of unstable sheaves. Secondly, we blow up these loci. All right. So in order to apply the technique of elementary modification, you need a divisor. You need to have a divisor. To get a divisor, we blow up. So and then after finite number of blow-offs and apply elementary modification. So after each blow-up, you find the subsheaf which is most responsible for instability. You apply elementary modification, you make it a quotient sheaf instead of a subsheaf. So after a finite number of these operations, you get a family of stable sheaves. So after finite number of blow-ups, you get M tilde, and it parameterizes stable sheaves to get a morphism to Simpson moduli. All right. And then third step is to analyze this morphism. So here, in here, the technique that we use is the variation of GIT quotients method by Thaddeus and Logachev Hu. Somehow these morphisms, there is some variation of GIT hidden inside this birational morphism. Okay, so how do you implement this strategy? So when d is equal to when d is equal to 1, it's just a Grassmannian, so there is nothing to do. When d is equal to 2, already this is not obvious. So the undefined locus here is the locus of stable maps to a line. So it's the locus of linear image. It's 2-to-1 map. Right. So the result is this. You start with M, Kusevich, you blow up along gamma. So this is actually a singular variety. It has Z2 quotient singularities. And the locus of singularities is gamma, exactly gamma. And you blow up, then you get a smooth variety. And then you blow down. And actually, this is the same thing as the variety of complete conics, relative complete conics. This is variety of complete conics. U over the Grassmannian GR, 3R plus 1. You choose a P2 in PR, and then over each P2 you get the variety of complete conics. So this is the fiber is a blow up of P5 along P2, variety of complete conics. So certainly you can contract this P2 part, and you get a P5 bundle over the Grassmannian. That's exactly the Hilbert scheme, and it's isomorphic to Simpson. So this is a fiber bundle over the Grassmannian, and the fiber is exactly P5. Okay, and actually there's one more contraction to the GIT quotient, P3R plus 2 SL2. There's one more blow down in this picture. How about degree 3 case? The locus of unstable sheaves has two irreducible components. Okay, so one component is the locus of stable maps to a line. Let me call this the locus of linear image. The other locus is gamma 2, which is the locus of the union of two, whose the locus of stable maps whose image is a union of two lines. Let me call this bilinear image. The locus bilinear image. So we have two unstable, two irreducible components of the locus of unstable sheaves. Well, the situation is a little bit complicated. That's not everything. So first of all, you blow up along gamma 1, which is a smooth for us in M. Then after the first blow up, you get a new locus of unstable sheaves. Okay, and so gamma 1 inside M, the normal bundle of gamma 1 inside M at each point F in gamma 1. That's precisely the projectivization of X1 over PR of the structure sheaf of line OL minus 1 and tensor product with C2. So this is the normal space to gamma 1. And then inside here, so you have two extension classes of OL by OL minus 1. Inside here, you have a locus of rank 1. Okay, two choices of extension classes which are linearly dependent. So that's just P, what is it? PR minus 2 cross P1. For this is vector space of dimension R minus 1, and this is C2, so you get projectivization of this. So gamma 3 is a PR minus 2 cross P1 bundle over gamma 1. So this appears in the first, this variety appears after blowing up M along gamma 1. Okay, so I can explain the theorem now. So now I can compare the conservative compactification and Simpson compactification like this. So theorem due to Chung and myself is this. So suppose X is a projective space PR and degree is equal to 3. We don't know about higher degree cases. We only know so far degree 2 and 3, 1 to 3. What is this? So we start with conservative, blow up along gamma 1, blow up along gamma 2, blow up along gamma 3. And after each blow up, you apply elementary modification along the exceptional divisors, and then make the sheaf more stable at each stage. And then you can check that after third blow up, everything becomes a stable sheaf. So you get a morphism to S. And then you analyze the morphism, and we show that this morphism factorizes into a sequence of 3 blowdowns, 3 contractions. We contract the proper transform of the exceptional divisor of the second blow up, contract the exceptional divisor of the third blow up, contract the exceptional divisor of the first blow up. And this is isomorphic to the Simpson compactification, and we show that Hilbert's compactification is a simple blow up. Okay? Right. And furthermore, we know that this can be further blown down to the GIT quotient of P4R plus 3 SL2. This is something called the quasi-map space. And if you blow up this variety along some sub-variety, which is the union of 3 transversal smooth sub-varieties, then if you blow up the quasi-map space, you get moduli of stable maps in this case. So basically, we know basically everything about this degree 3 case. Okay, so this has been something that we reported last December. So new result is the case when target is projective homogeneous variety. So it doesn't have to be projective homogeneous variety. There's a couple of conditions that X should satisfy in order to have this result. Okay. The theorem is that, theorem due to Chung and myself, is this. Exactly the same result holds for projective homogeneous varieties. Projective homogeneous varieties. For homogeneous variety. Oh, sorry, for degree less than or equal to 3. Degree 2 or 3. Exactly the same sequence of blow-ups, sequence of blow-downs. And the same picture is exactly the same. What is good? Okay, an application of this is this corollary. We can really calculate all the Betti numbers of these compactifications. Hilbert compactification, Simpson compactification, from the Betti numbers of the stable map space. How can we do that? So luckily, this year, I think last year, we found a paper of a student of Andrew Crash from Switzerland who calculated the Betti numbers of the stable map space for for the case when X is a Grassmannian. So a student of Andrew Crash, his name is A. Martin, he calculated the Betti numbers of conservative modular space by using circle action on M, localization phenomenon. And then, so because M, H, S are related by explicit blow-ups, we can calculate all the Betti numbers of H and S. Possibly we can calculate all the intersection numbers of H and S and so on, starting from the knowledge about the stable map space. Okay, I don't want to show you the precise formula because it's quite complicated. It's about 7 or 8 lines long. Okay, thank you very much. I'll stop here.
Are there